VLSI in the terms of electronics. So connecting all the transistors or electronic components, resistors, capacitors, diodes, all these components together to create an application or to create a programmable IC integrated circuit, that is called VLSI. So VLSI is nothing but very large scale. We are connecting very large number of electronic components. Okay. So before VLSI, what we have? We have LSI, MSI, and SI. Small scale integration, medium scale integration, large scale integration, and very large scale integration. And in the future, we have ULSI also, ultra large scale integration. So that are with a nanometer of 5 nanometer and 7 nanometer, where 1 lakh millions of transistors are sitting on a single IC chip. Okay. So what is the use of VLSI? So basically using VLSI, okay. So we are designing circuits, chips, and integrating them on a single silicon design. Introduction. So if you are taking any case study, okay, about a project in VLSI, so what we will get from the customer first? We will get from the customer about his requirements. Then for his requirements, we will ask for the specifications. What are the specifications you want me to design for your required design? Then we'll go for the implementation part. Then in the implementation part, we will understand how to do the design. That means, for example, we have a Bluetooth chip. So in Bluetooth chip, we have transmitter and receiver. And if it is a battery source, we have battery source. And if you have a charger, we'll have a charging port. So that means we have power unit, transmitter, receiver, and clock circuit. Clock circuit is nothing but PL. So these are the 3 blocks or 4 blocks we have to build as per the specification. And the implementation part, what we'll do? As we know, circuit analysis, as we know, digital analysis, digital design. Okay, we'll go for the design of circuit based on its implementation part. If it is a PLL, we'll draw the PLL circuit. If it is a clock generator circuit, we'll write the code in Verilog and generate the clock with a certain frequency, ADPLL. And if we have a transmitter and receiver, we know the LNA, transmitter and receiver. Based on that, we'll implement the design. And next is validation. What type of validation we do? Design validation, whether it is meeting our specifications or not. If that is meeting our specification, we'll ask the customer to buy your design from us. Once he buy our design, okay, we are paid with the market challenging amount, and we are ready to release this chip into the market. Clear? So VLSI design. So VLSI design starts with a formal specification of a VLS chip, follows a series of steps, and eventually produces a packaged chip. So from the specifications to the packaged chip, okay, each and every flow of VLSI design has job opportunities. The top level architecture or the customer is the person or the other company or the client who gives us the specifications, and the client one who buys this packaged chip from the designer. So who are the designers? We are the designers. So packaged chip is nothing but completely integrated on the board with connected interfaces. So that is what the meaning of packaged chip. Next is simplified VLSI design. So in the simplified VLSI design flow, we have system specifications. Okay, Bluetooth chip, functional architectural design. Okay, so we will draw the block diagram. Okay, the block diagram specifies this is my Bluetooth chip. This Bluetooth chip has PLL, phase lock loop. Okay, power unit, transmitter, and receiver. So this is my system specifications. For this system specifications, I have given a block level diagram. Using this block level diagram, we will write the code or we will design the circuit using behavioral representation. If it is analog block, we'll write the circuit. If it is digital block, we will design the Verilog code. Okay, as it is completely VLSI ASIC design flow. So we are into digital design flow only. So then we'll complete the functional verification. Using the functional verification, we will pass the test bench to our design. So if this is passed, we'll go for logic design. So in the part of logic design, we have synthesis, PNR, placement and routing. Once this is done, what we will go? We will go for backend. This is verification. Next is circuit design. If it is a circuit part, this is physical design, and this is circuit design. So in the circuit design, we'll design the circuit. We'll verify the circuit by designing a analog test bench. And once the circuit is passed, we'll go for layout design using physical design and custom layout design also. And next is physical verification. Physical verification is nothing but countering GDS to submission ready. Physical verification, once it is passed, we are submitting this chip for fabs, for chip design or chip fabrication. 4 levels of design representation. Okay, we have behavioral representation, we have block diagram. Logical representation, we have circuit diagram, like digital circuits. And in the terms of analog part, we have transistor or MOSFET level circuit. As a VLSI chip design engineer, we have to go for physical design or analog layout. Then we call it layout design. This is most detailed part of VLSI design flow: system specification, architectural functional verification or architectural design. This is all front end till here to here, logical verification. Next, this is circuit design. So circuit design is nothing but it is analog front end, circuit design and circuit verification. After these 2 phases completes, we'll go for layout design and physical design. Once these 2 phases are finished, we'll go for fabrication and testing. So we have 2 types of design methodologies for digital design. Even in analog circuit also, we follow the same thing. Either top-down design methodologies or bottom-up design methodologies. So top-down design methodologies, using the diagram, I will explain it. So we will have the top level block. We'll split this top level block into sub blocks. Okay. Consider example of Bluetooth. Okay, this is my top level block. So here what I will have in the Bluetooth sub block 1, PL. This is power unit, power supply unit. Here I have TX and RX, transmitter and receiver. So coming to PLL, in the leaf level cells, we have voltage controlled oscillator, charge pump, filter. Okay, these are the leaf cells. And here we have clock divider circuit for dividing the clock for a certain frequency. In the subblocks of power unit, we will have SMPS or charge circuit, whatever. Next, in the transmitter and receiver, we will have LNA, TX, low noise amplifier, LNA, RX, low noise amplifier, LNA. So from the top level block, okay, Bluetooth, we have split subblocks PLL, power unit, and TX and RX. And in the subblocks, we have another split to the leaf level cells, receiver, charge pump, filter, clock divider, SMPS, charge circuit, LNA, TX, and RX. So this is how we break down the design and integrate together to form a top level block. What is the main purpose of leaf level cells? So leaf level, see, it is not possible Narendra Modi to look after Hyderabad. Okay, so we have our own assembly. So in assembly, we have Chief Minister Revant Reddy. So Chief Minister will report to Prime Minister and President about our state. The same way, we have leaf cells. So the leaf cells are the very small blocks. Combining these leaf cells, we will get a subblocks and subblocks together to form a top level block. Sri Lakshmi, Sai Lakshmi, Tarak. Tarak, did you understand? We are splitting a big block into smaller particles and designing them. And altogether, smaller blocks, we are integrating on the top level block to form a big design. So for a team of VLSI engineers, it is not possible for 4 engineers to complete the design very quickly on the top level. So we will have 10 to 15 engineers in a team. All the 10 to 15 engineers will be working on the sub blocks, leaf level blocks, and the manager will be sitting on the top level. Clear? I can move further. Tarak, Sai Lakshmi. Yes, sir. Next is bottom up. So bottom up, what we will do? Already we have some leaf level cells. Those are like macros. So if I want to design a SoC, system on chip, consider ARM processor. Okay, so the leaf level cells are memory, flash memory, and this is ROM memory, and this is serial communication protocols. Serial communication, sorry, SPF, I2C. UART. And this is APB. Bridge. And this is AHB. And this is system bus. And the macro cell top level subblock, it is AXI. And here period form. And here we have flash. So I am using a top level SoC ARM processor design. So in this ARM processor design, I have all these modules. So what I will do, I will be buying it from other vendor, or I will be designing it from the other team macros in the form of macros. These macros will directly integrate in the top level. These macros has leaf level cells. If you go for flash memory, we'll have RAM and ROM. If you go for serial communication, we'll have serial peripheral interface, inter-integrated circuit I2C, UART, universal asynchronous receiver and transmitter, and advanced peripheral bus bridge for serial communication. And if you go for system design, okay, we'll have advanced high performance bus and system bus. Apart from this, we'll have AMBA bus protocol. Advanced microcontroller bus architecture. So whatever the ARM processor we take, so ARM processor is famous for AMBA bus. Okay. So this is how we will go for bottom-up design methodology. Hope everyone is clear. Everyone followed? Tara, Bhuvaneshwari. Keshava, JD. Yeah, right. Thank you. Next is simplified view of VLSI design flow. So this is top-down algorithm and this is bottom-up algorithm. So in bottom-up, we'll have the macros form. So in that macros form, we'll integrate and we'll design a top-level block. And from the top level, we will have the specifications. We are going to build those macros. Next is Y chart. So Y chart is nothing but we have three domains: structural domain, behavioral domain, and geometrical layout domain. So in behavioral domain, we'll have algorithm. We'll build a flowchart. The flowchart is called finite state machine. For that finite state machine, we'll define module description and Boolean equations, and we'll write the logic and coding for synthesis. This is behavioral domain. Next, if we have structural domain, we will have an example processor. In that processor, we will have registers like ALU. In ALU, we will have operations related to arithmetic, logical, and other calculations. So for this, we will have a transistor level circuit diagram. So doing all these things, we will do chip floor plan and we will do the placement of the cells and we will run the layout of the design. And this is all we do the geometrical, like graphical way. So we'll generate at last the mask. That is nothing but chip. So as we have discussed system specifications, what are the system specifications? Consists of performance, functionality, physical dimensions, okay, design technique, fabrication and technology. Sir, why we have to learn Y chart? What is its importance? So whether you follow structural domain or whether you follow behavioral domain, okay, so you have to complete your chip to close it in a geometrical domain. Pabya. Okay. So you have an algorithm. For that algorithm, you are writing a finite state machine. Using that finite state machine, you are building a FSM based compute logic design. For that logic design, you are having leaf level cells and Boolean equations. And at last, you will have the transistors with that leaf cells. Using these transistors, we will do floor plan, placement, clock tree synthesis, routing, and physical verification, and do the chip level mask design. Clear, Bhavya? Okay. So system specification. What does system specifications consist of? The system specifications related to performance. That is nothing but clock frequency. Functionality. About what we are going to design the project. Next is physical dimensions. What should be my chip size? And design techniques. What design technique we are going to use? And fabrication technology. Which technology node we are going to use? That means we are using TSMC, UMC, Global Foundries, or XFab, or Intel Fab, or Samsung Fab, whichever the fab we are using. So using that, we have to do the fabrication. So system specifications related to size, speed, power, and functionality of the VLSI. This will give you the basic architecture. So functional design. Functional design will have behavioral modeling, interconnects, input, output, timing about each block. Next is logic design. Logic design is nothing but writing your block level design into a logical design using RTL programming. That is hardware description languages using Verilog or VHDL. Apart from analog, digital part, if you have gates or Boolean or Verilog, so the other part is circuit design. We will have gates and transistors. So this is how we cover a system design. Next is physical design. Physical design, we have few steps. Those are called PNR. PNR is nothing but placement, floor plan, placement, CTS, routing, physical verification, GDS to submission. So this is PNR, physical design. So overall design process, we will cover this much. So if it is circuit design, we will place the transistors, we will move the placement of the transistors or the MOSFETs. And if there is a clock net, we will do the clock net routing and signal nets routing. And at last, we will go for physical verification for checking DRC, design rule check, LVS, layout versus schematic, and PEX, parasitic extraction format. And doing all this, we will do at last, taking the output of physical verification results, we will back annotate it to design for functional verification. Once the functional verification is passed, we will generate the GDS2 file. Clear so far, everyone? Were you able to follow, everyone? This is a recap. Yes. So overall design process. So we have complete design process here. So using this design process, what are the tools used in the market? I'll tell you. So the person who deals about architecture, those people will use the tools. Those people will give you the specifications, or they will define the logical diagram of the circuit using text editor or C compiler. And the next task is logic design. So logic design will come under behavioral simulation, coding, logical simulation, testing, verification. Next is synthesis. Next is data path schematics. They will draw the schematic part. So the tools are from the RTL simulator, synthesis tools, timing analyzer, power estimate. Circuit design. As a part of circuit design, we will design cell libraries, we will design circuit schematics, we will perform functional verification for circuit simulations, and we will design mega blocks for macros. So the tools used are schematic editors, circuit simulators, and circuit design routing skills. Next is physical designer. Physical designer is the one who takes the design from the logical designer or circuit designer, perform the placement, routing, okay, and layout generation, and completes the physical verification using DRC, LVSI, ERC, and PEX. ERC is nothing but electrical rule check. So these are our foundry checks. Foundry checks means fabrication checks. So we'll use place and route tools, physical design tools, and evaluation tools. Clear, everyone? So far? Yes, sir. So coming down into the deep into the subject, in the logic design, we have combinational logic design. So combinational logic design is a fundamental concept of digital electronics. Okay. So the output depends upon the current state. Whatever the inputs we give, it operates and gives us the output. For example, we have the basic gates, AND gate, OR gate, NOT gate. So we know the AND gate, if two inputs are high or low, okay. If two inputs are high, then we get the high output, else we will get the low output. It is like multiplication, AND gate. OR gate is like addition. And NOT gate is like complement, reciprocity. And NAND gate is a reverse of AND gate, negation of AND gate. NOR gate is negation of OR gate, and XOR gate is exclusive OR. It is A B bar plus B A bar. So that is the equation for XOR gate. So when the two variables are non-similar, A or B, then the output is high in the XOR gate. So this is combinational logic gates, basic gates. And apart from the combinational logic gates, we have Boolean algebra. So using Boolean algebra also, we will solve the logical expressions like identity law, null law, idempotent law, complement law, commutative law, associative law, distributive law, and De Morgan's theorem. So whenever we want to reduce the logic or optimize the logic, okay, we will use this Boolean algebra expressions or theorems, techniques to reduce or optimize the logic. So at the time of optimization, when we are doing synthesis, when we are doing placement, when we are doing routing, when we are doing clock tree synthesis, what we are doing? We are pressing the button or we are giving the command synthesize underscore optimize. At that instance of time, my tool does optimization based on its mathematical calculation using Boolean logic to reduce the logic to yours meet us function. This is how optimization techniques are achieved using Boolean logic. So combinational circuits, we have different combinational circuits like decoders, encoders. So in concept of binary encoder, we have 8 to 3 encoder, binary encoder. So we will have 8 inputs and 3 outputs. So based on the encoding line, the output is driven. So the channel, if I want to encode D4, okay, D2, D3, D4, okay, what will be my output? If D4 is 1, the output is 100. Okay, so this is how we decode or encode using combinational logic. So the decoder is the reverse of encoder, which has 3 input lines and 8 output lines. So whatever the vectors we pass on the 3 input line, we have to decode on the 8 output. So basically, these decoders and encoders are mainly used in display screens. Okay, next is multiplexers and demultiplexers. Multiplexers and demultiplexers are another set of combinational logic design. We have 2:1 multiplexers, 4:1 multiplexers, 8:1 multiplexers, and in the same way, demultiplexers, vice versa. So multiplexers have example 2:1 multiplexers have 2 inputs, 1 output based on the select line. If the select line is 0, it will send the output 0. If the select line is 1, it will select the select line depending on the first line. The same way we operate using our TV channels. So TV channels, we have n number of TV channels receiving on our dish TV, but the output is selected on the remote or the controller, but we are able to see only one screen. Okay, this is example of multiplexer. Demultiplexer is nothing but from the single point we are distributing it to multiple points. Like broadband, we have 1 gigahertz speed of laser line. We want to split, okay, 110 megahertz lines. Then only we can do using demultiplexer. So there we will have demux. So another set of combinational logic design is adders. So far it's clear, right? Logic design. Is everyone in the class? Tarak, Rambabu, JD. Yeah, Tarak, you have any doubt? Anushka, Chakrapani, Jansi. No doubts. Could we proceed further? Yes. So another set of combinational logic designs we have. Those are adders. So in adders we have half adders, full adders. So half adder is designed using one XOR gate and one AND gate. So the Boolean expression of half adder is sum equal to A XOR B and carry out equal to A dot B, that is A and B. So this is functional expression of half adder. So truth table of half adder. If you are giving 0 0, the sum is 0, carry is 0. And if A and B are non-similar, the operation 0 plus 1, 1, 1 plus 0, 1. But whereas coming to 1 plus 1, sum is 0 and carry is 1. Why? Because 1 plus 1 is 2. So what? How we will be writing 2 in the binary? 1 0. Okay. So sum is 0, carry is 1. In case of 1 plus 1. This is how binary addition will happen. Next is full adder. Full adder is a combination of two half adders. So this is top level block and these are two sub blocks. Okay, and the leaf level blocks are XOR gate, AND gate, and OR gate. Got it, everyone? This is top-down design methodology. So if I start writing code, I have a ready-made code for OR gate, AND gate, XOR gate. How I want to connect them? Using nets. Then I can build a two half adders, sub blocks, and connecting these two half adders. Okay, using nets, I can build a full adder. Clear? The another set of combinational circuit is half subtractor and full subtractor. So half subtractor, okay, we have difference and borrow. So difference is equal to A XOR B and borrow equal to A and B with a negation of A. Next is full subtractor. Full subtractor is a combination of two half subtractors with OR gate integrated. Next is digital design through Verilog. So everyone is clear with combinational part? If you have any questions, please let me know. Any questions? These all are your engineering subjects, but as a part of VLSI training course, we have to understand each and every concept, and in detail we have learned in the previous sessions. So this is a recap session, so I am going it very fast pace. Hope you are clear, everyone. Right. Next is digital design through Verilog. So as a logic design, we would most likely to prefer to write codes using hardware description language. So we have two sets of hardware description language. One is Verilog and the other one is VHDL. So does anyone know the full form of VHDL? HDL is hardware description language, but what is the full form of VHDL? HDL is hardware description language. Verilog is another hardware description language. Okay, if we elaborate VHDL, the full form is VHSICHDL. Okay, this is the full form of, yeah, correct, Bhuneshwari. So this is the full form of VHDL, exactly, VHSIC. very high speed integrated circuit hardware description language. Yeah, correct. So we have two types of hardware description languages. One is Verilog and another one is VHDL. So the students, the engineers who are familiar with C programming language, most of the times they prefer Verilog. C programming is similar to Verilog. The constructs, the methods, whatever we write in C programming, but C programming is a software programming language, but Verilog is a hardware programming language. Verilog is used for modeling, designing, and verifying digital systems and circuits. So we have tested two possibilities using Verilog. So we have written a Verilog code and we have written a test bench in Verilog English, and we have passed functional verification. And another set of verification we have done. We have written a Verilog code. We have created analog test bench using circuit, and we have done the simulation. That is analog mixed signal simulation. So Verilog is user friendly, and the tools have inbuilt Verilog libraries, and whatever the library sells, fabrication, PDKs, whatever we use, they have inbuilt libraries for Verilog and even for VHDL. And the persons or the participants or the students or the engineers who are familiar with VHDL, they will go with VHDL. So as a user friendly, I am familiar with C language. So I am going with Verilog. So it allows designers to describe the behavior, structure, and electronic system. So whatever you design, you will explain the behavior, you'll explain the structural, or you'll explain the method of logic of your electronic circuit system, whatever you want to build using Verilog HDL. So we have levels of descriptions using Verilog. Verilog supports three methodologies: behavioral modeling, data flow modeling, structural or gate level modeling. And the last one is switcher transistor level design. Switcher transistor level design, we will use it mainly for analog mixed signal simulations. Okay. Hope everyone is clear so far. We'll continue further. Someone please reply. Yes, JD. So there are two different flows. We have ASIC and we have FPGA. FPGA is the full form for field programmable gate array, and ASIC is application specific integrated circuit. In case of ASIC, okay, chip is one time program, whereas FPGA, the name itself tells us we have field programmable gate arrays. So we can code this FPGA multiple times. Whereas FPGA, the system is huge in circuitry, whereas ASIC, the system is very, very minute and small in size. So when we want to build an ASIC, we can test on FPGA logically. If we want to go to test on the physical wafer or anything, we need to have emulators. So like that emulators we have from the Cadence Palladium. Palladium, those are emulators which will work for ASIC design testability. Give me a minute. Yeah, Kishore, Krishna, Tarak, my audio is clear. I took a small break for 1 minute. It is raining heavily. So I just wanted to close windows. So let's continue. So we are understanding about FPGA and ASIC. So when we want to design a ASIC chip, it is only one-time program. That is directly we are doing the layout and GDS. And whereas FPGA is like a microcontroller board, we have field programmable gate arrays where we can upload our logical Verilog code after synthesis. Okay, we can do the place and route netlist and we can check the behavior. Whereas if we want to check the behavior of ASIC circuit chip, we have a different emulators called Palladium from Cadence. Clear? So the delivery time for FPGA is very fast and the delivery time for ASIC is very late. Why? Because we have to submit our soft copy of chip to the foundry. Foundry will take some time, nearly 45 to 50 days. Okay. They have to manufacture it on the wafer. Usually we don't have wafer manufacturing in India. Okay. We have in America, Belgium, Canada, Singapore. Okay. So the wafer will get manufactured there and it will take almost 15 to 20 days for transit. Okay. This is how ASIC chips are manufactured in foundries. So if you want to get the jobs in foundry level also, there are some EDA tools like device modeling. You need to know about device modeling. So there are some tools, Silvaco, TCAD, TCAD Centarius, TCAD Centarius Test Bench. So we need to design the devices by doping, by creating the terminals for a MOSFET, which metal we have to use for gate off, which metal we have to use for source, drain, poly oxide. All these properties we are going to define in a code format in TCAD or Silvaco. This is all about device modeling. So the people are applied physics. This is also called as applied physics sometimes. Okay. So the people or the students who are interested on these subjects can learn these tools in their MTechs or in PhD or in any higher educations in the tier 1 colleges and get the jobs in foundries like Global Foundries, Samsung, Intel, XFAB, TSMC, UMC, XME, and all these things. These are all the foundries. Okay. So using Verilog in ASIC part, we can cover only synthesis. Whereas in FPGA part, we can continue synthesis. We can go for place and route on the PLS, programmable logic arrays, and we can download the circuit. We can verify the circuit on the FPGA board. We cannot test all the ASIC circuits on the FPGA boards. Okay. So FPGA board or whatever the IC sitting on the FPGA board. Okay. Xilinx processor or AMD processor. Okay. ASIC chip. That is also an ASIC chip. But those are programmable. Similar like our 8051 microcontroller, Arduino Uno board, ATmega328 microcontroller, or ARM microcontroller, LPC2168. Okay. The same way we have FPGA boards. Clear so far, everyone? Yes, Bhargav. Thank you. If you have any questions, please let me know. So now we will understand how the Verilog programming starts. In C programming, what we will do? As include stdio.h, printf, hello C world. The same way we have void main, module, adder, and inputs and outputs. and some statements for computation, and next end module. So similar, I'll write a code for C and Verilog in comparison. Void main BA comma B comma C. Enter. C equal to okay. In the same way, I'll try to write Verilog. Audio of subtractor A comma B comma sum comma carry out. Now I have to declare input B comma B output sum comma carry. Okay. Assign sum equal to A XOR B. Assign carry equal to A and B. And module. So void main is the start of the C programming. Okay. So we have flower brackets. Same way we have module and end module for flower brackets in the case of Verilog. We have initialization of variables int A comma B comma C. And we have input variables and output variables. In case of Verilog, as this is a hardware description language and that is a software description language. So inputs are A comma B, outputs comma sum comma carry out. So we are assigning sum equal to A XOR B using Verilog data flow method. Okay. Carry equal to A and B and end module. So that is using C programming. Can we get logical gates as the output if we synthesize? No. But if we synthesize Verilog code, we will get XOR gate, AND gate, and nets and wires connections. So only the constructs of C language are used in Verilog on the high level part. But C is a software programming language and Verilog is a hardware programming language. Clear? Hope everyone is understood with this Verilog module. Right. Thank you. So language constructs and conventions. So module and end module are the keywords. Begin, end, if, while are the keywords. Next is identifiers. What are the identifiers? Identifiers are like operators or variables. Identifiers or the special characters. Those are identifiers. And module, input, output, assign, end module are the keywords. Here you can see in the right side. Identifiers, keywords. Identifiers are module name, comparator, and keywords are module input, output, assign, end module. And what are the variables? X, Y, Z. These are also identifiers. Next is white space characters. White space characters are nothing but new line, new tab, new space. And we have three different logical values in Verilog: 0, 1, X, and Z. X is unknown logical value, either 0 or 1. And Z is high impedance state, which is floating state. We cannot determine the value. So we have Verilog operators related to arithmetic operators and add, subtract, multiply, divide, modulus. Modulus will give you the remainder value. In bitwise operators, which performs on each and every bit with the preceding bit. Okay. Next is logical operator. Logical operator is output is Boolean. And whereas the bitwise operator, the output or the return type is value. And arithmetic operator, the output or return type value is value. So we have different kinds of operators like concatenation operator, arithmetic operator, modulus operator, okay, relational operator, logical operators, logical equality, inequality, case equal to, case inequality, conditional operator, if else, bitwise operator, reduction operators, and shift operators. So we have learned in our previous sessions using examples and writing them in the Verilog code. So I have floated an assignment for you people to use these operators and design a Verilog code using all these operators. Next, we have data types. So we have data types like net, variables, input variable or output variable. Net is connectivity. Wire is connectivity. Register is data storing element. Okay. As we have seen, there are three types of modeling in Verilog: gate level modeling, data flow modeling, and behavioral modeling. So gate level modeling or structural modeling is we have description of the gates. For these gates connecting the code using primitives, we perform a gate level Verilog code. So module, multiplexer. Okay, we'll write gate for A0, gate A2, A1, A3, and connections in 0, in 1, in 2, S0, S1, and output out. So we'll write the gate level or structural modeling code in this way. This is simple structural code where we use primitives. Primitives are nothing but standard basic gates: AND gate, NOR gate, XOR gate, XNOR gate, buffer, inverter. All these gates are standard basic gates. And apart from this, we have typical cells like buffif, buffif 0, buffif 1, not if 0, not if 1. Based on the control input control signal, okay, so the input follows the output, that is buffer. It's simple like tri-state buffer. Clear everyone so far? Correct? Yes, sir. So gate level modeling of half adder. Module half adder. Sum carry in 0 in 1. Outputs are carry and sum. Inputs are in 0 and in 1. So what is my sum? XOR. I am writing XOR of 1. Sum in 0 in 1. First we have to put output signal, next followed by input signals. Carry equal to and of 1. So and is a primitive, and of 1 is the function calling this primitive. Carry in 0 in 1. End module. So we have defined a test bench to pass values, module, test bench half adder. So inputs and outputs will become registers and wires, and followed by connections for the signals from the design under test and test bench. So I am passing the values in 0 equal to 0, in 1 equal to 0. With 10 units of delay, I am passing another set of values 0, 1, 1, 0, 1, 1. And I am printing all the values using $display. Sum and carry. And once the $finish comes, it will end all the delays. So here we have delay of 10 seconds. To execute this, we will have 10 plus 10, 20. And to execute this statement, we have 10 plus 10 plus 10, 30. And to execute this statement, we have 10 plus 10 plus 10, 40. And at the 40 units of clock cycle, we will get the output for in equal to 0, 0, 0, 1, 0, 1, 0, 1, 1. And $finish will end the clock period for 40 clock cycles and end module. So this is the test bench description for a gate level memory. And we have different types of gate delays like rise delay, fall delay, turn off delay. So if you want to put those gate delays, okay, so we have to use hash. Clear? Next is behavioral modeling. Behavioral modeling is nothing but explaining the behavior of your circuit. So behavioral modeling constructs follows basically two kinds of statements, always, initial. Always is a event triggered statement. Initial is the initialization of values. See, here is a behavioral example code. Module behave. Register 1 down to 0 is 2 bits, A is 2 bits and B is 2 bits. So I'm initially passing the values for A 1, B equal to 0. Always, okay, every 50 units of time, A equal to negation of A. That means for every 50 units of delay, A value becomes negation. So this is my clock cycle. This is having 50 units of delay. Okay. So I am passing A value 1. So it will be 1. Okay. So after 50 units of time, it will become 0 for another clock cycle. And for another clock cycle, it will become 1 again. So this will completely toggle for every 50 units of time. And always hash 100 B equal to negation of B. So 100 units of time B equal to negation 1. So here we are using the constructs of initial and always. So it is called behavioral modeling coding. And in real time, we don't see always it is a behavioral, always it is a data flow, always it is a gate level. We have mixed mode. Okay. Practically, we will use mixed mode kind of Verilog coding. Clear so far, everyone? Tarak, Sunita, Bhuneshwar. Yes. So procedural assignments. So there are two types of procedural assignments: continuous assignments and non-blocking and blocking assignments. Procedural assignments are for updating integer, register, time, memory variables. Continuous assignments drive next variables evaluated and updated when an input operand changes its values. So for this reason, we are using blocking assignments and non-blocking assignments. So blocking assignments means I have a value variable a equal to 10. Unless until this 10 value is assigned to a value, okay, it will not execute the next statement. Whereas non-blocking assignments, a equal to 11, b equal to 4. So there is no blockage in the delay. So this statement will execute in one clock cycle and this statement will execute in the same clock cycle. So there is no blocking between variables a and b. This is non-blocking assignment. There is only symbol represented, that is equal to greater than. So this is non-blocking assignment and this is blocking assignment. LHS equal to RHS is blocking. LHS using this symbol equal to RHS is non-blocking. Clear? We have conditional statements like if else, case, and procedures, initial, always, task, functions. So these all are under behavioral modeling of Verilog. Okay. So if else is the thing, but if we have expression and set of statements to execute. If the statement is true, it will execute the next set of statements. If the statement is false, it will go to else block. If else block is true, okay, it will execute the else block statements, else it will go to the end of if else statements. Next is case. So we have certain n number of test cases to test. Okay. So I want to design a calculator using Verilog operators. Okay. Then what I will be doing? For addition, plus. For subtraction, minus. For multiplication, star. For division, modulus. In this way, I'll assign for each and every case value one operation. I'll design a calculator using case expression. And the syntax is case, end case. And for each and every operation, we have begin and end, begin and end, begin and end, begin and end. Similar like function, closing braces and open braces in our C language. Next, we have procedures. So we have procedural statements in behavioral modeling like initial, always, task, function. Initial and begin values. Initial is nothing but initialization, the initial state of what variables should hold the values. So always is an event trigger. Always at the rate of positive edge of clock. Always at the rate of B event. B is the variable. So if B value is 0 or B value is 1, what will happen? That we have to write using always. Task is nothing but we want to perform small amount of task. Like in the middle of the code, I am writing a task. Which is similar to function. Okay. So I can write the definition of the task. I can execute there itself. But whereas for a function, I have a called function and calling function. Called function is a different module and calling function is instantiated in the main function or main Verilog. But task, there itself we can define and there itself we can run the task in the Verilog code. So this is the example of always at the rate of event trigger. And the events are called as sensitivity list. Next is looping statements. So we have looping statements like while, do while, and forever. Forever is a looping statement used in Verilog. So forever, begin, end. This is a syntax. So for a free running clock, for every 5 units of delay, forever hash 5 equal to clock negation of the clock. So this will generate a continuous clock. Unless until I write a $finish. At what time I am writing $finish? 100 units of clock. What will be my clock pulse? It will be 20 times. And the duty cycle is 5 units. And the clock period is 10 units. And it will run for 20 times. Clear? Everyone able to understand? Tarak, Abhi, Sunita. Yes, Bhuvaneshwari. Thank you. Any questions? Please let me know. So these all are revision part. So next is sequential circuits. So we have covered ASIC design flow for digital part, analog part, and FPGA design flow, and understanding the top level design methodology, bottom up design methodology, and combinational circuits, and Verilog introduction, and understanding the basic modeling of Verilog, data flow, structural, and behavioral. Next is sequential. Sequential circuits are the combinational circuits with memory element. Okay. So sequential logic cells will depend on the inputs and previous state values. Okay. It's like human relations. So human relations will depend on current state and a previous state. So previous state, whether we have friends or not, we have relatives or not. We have relatives, and current state, we have current state, like that. So sequential logic circuits are digital circuits that store and use the previous state information to determine their next state. Unlike combinational circuits, which only depend on the current input value or the current state to produce output, sequential circuits depends on the both current state input values and previous state stored values. So to store those values, we use a concept called memory element. Sequence circuits are commonly used in digital systems to implement state machines, finite state machines, timers, counters, memory designs, flip-flops. So all these are used to design sequential logical circuits. There are two types of sequential logic circuits: finite state machine, synchronous sequential circuits. So finite state machines are FSMs are designed to have a limited number of states and are typically used to implement state machines and control systems. So as an example of FSM, we have discussed about escalator or a lift, 5-story building, 10-story building. What are the states? So we have inputs. The states are nothing but floors. So we have level 0, level 1, level 2, level 3, level 4, level 5. These all are floors. And we have two sets of inputs. The current input is output outside person, and the previous input is the inside person. And initial state we have to declare where it is in which floor, or we are resetting that to reach to the ground floor or the top floor. Okay, this is how we design an FSM for escalator or lift. Hope you got the example, right? Next is synchronous. So synchronous circuits are of infinite states or infinite number of times of computation depending on the inputs and previous states. Like examples, timers, counters, memories. Sequential circuits produce an output based on current input and previous output variable. That means sequential circuit include memory element that are capable of storing binary information. So that previous value is stored in the memory element as a binary value. Next, we have types of sequential circuits that are asynchronous sequential circuits. These circuits do not use clock signal, but uses the pulse of the inputs just for an event trigger. Whereas synchronous circuits, they will use continuous clock signals as a pulse to generate. Dependent on the clock, we will drive the outputs in synchronous. We will have clock signal based on the event. We get the output in asynchronous. But whereas based on the clock period, synchronous, on the every state, we will get the output signal. This is synchronous, this is asynchronous. Asynchronous circuits are faster than synchronous circuits. Next is synchronous sequence circuits. These circuits use clock signals and level input. Okay, the output pulse is same duration as the clock pulsar, Okay, so if we are passing the clock of 50 nanoseconds and the outputs also follows dependent on the clock signal, the 50 seconds. So synchronous circuits are a bit slower than asynchronous circuits. When we want to approach the design with faster computation, we go for asynchronous. When we want to go with synchronous, okay, dependent on the clock, then we will go for synchronous design circuits. As a part of sequential logics, we have latch and flip-flop. So latch is level triggered and flip-flop is edge triggered. So we have different types of flip-flops and latches: SR, D, JK, and T. So based on their functionalities, we have truth tables and their logical diagrams. So if the clock is level triggered, we'll go for latches. If the clock is edge triggered, we'll go for the design of a flip-flop. A flip-flop is a circuit that maintains state until directed by input to change the state. Okay. So the basic flip-flops are constructed using normal combinational logic gates. Even latches also. Both are same. Okay. So here we call as clock, here we call as enable. So I'll explain about one flip-flop. It follows the similar functionality on the edge triggered and level triggered if it is a latch. So the output of SR flip-flop is set and reset. JK flip-flop is master slave flip-flop. Okay. Slave has to follow master. And whereas D flip-flop, input follows output with a clock delay and cell delay. Whereas T flip-flop is toggle flip-flop. It is, if it is 0, the output is 1. And the 1, if the input is 1, the output is 0. Using these sequential logic circuits, flip-flops and latches, we build digital circuits in sequential model like counters, up counters, down counters, asynchronous counters, synchronous counters. Okay, ring counter, general purpose registers like shift registers. So in the shift registers, we have different types like serial in, serial out, serial in, parallel out, parallel in, parallel out. Okay, and bidirectional shift registers, universal shift registers, and shift registers with counters. So how many bits we have shifted, left shift or right shift? Okay, and how many bits we are counting? This is the functionality of shift register counter. This we use in serial communication bus protocols. Okay, any questions? If there are no questions, either you must be understanding everything or you are not understanding anything. As this is a revision, okay, already we have learned these concepts. Okay, so we are very familiar. In the detailed classes, we have deep dived the logic also. Understand the counter, wind counter, shift registers, and all those things. We have wrote a code for shift register serial in parallel, and we have completed using serial communication physical design also. Okay. Hindu Kumar. Sir, you said you will share what are the online platforms for learning VLSI courses. Online platform for learning VLSI course. Hindu Kumar, I didn't tell these online platforms for learning VLSI courses, but I have told you what are the tools we can use online for running VLSI course. Okay, so courses I am not aware. Online courses, even I have to check online courses. Okay, so online course I'm not aware. Online media tools. We can use PDA Playground, basic one, Xilinx, ISC, we've added. Modern SIM. These are the basic for digital. And someone has suggested me micro for circuit. I have never used microwave. Okay. So this is going for Kavya Sri. Sorry. It is for everyone. And coming to the tools of commercial part, like cadence or synopsis or mental graphics. So I'll better prepare a table. So I can import a table. Is this a PDF or so let me one add one slide here and take a table. So, three columns. So here we have role, windows, synopsis. For logic design, Xcelium, or Xcelium is also called as Xrun. Iron, synopsis, Verilog compiled simulator, VCS, logic design, verification. Next is synthesis. Genus. In synopsis, we have DC compiler, design compiler. Formal verification, we have conformal, not aware about synopsis formal verification tool. Let us check in internet. Formality. 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 Physical design in ours ICC or ICC 2. Next is circuit design, impedance, IC 618, IC 231, purchasing. Chances are I am speaking very low voice. From synopsis, custom compile. From designer for circuit design. And next is circuit verification tools are ADE, Spectre. Here, not aware of synopsis. Circuit synopsis, circuit verification tools. Circuit simulator. Prime sim. Okay. Next is timing. Campus. Prime time. Power. Voltage. Prime power. Physical verification. We have Akura. Qantas. QRC. Okay. From synopsis, we have star. Stars. And apart from this physical verification, we use a famous tool from vendor graphics. Okay. Siemens vendor graphics, famous tool, Caliber. So once after these completes, we'll generate the GDS file and submit it to founder. Got it? Everyone understood clearly? So tools, logic design, and these all are the steps of our ASIC design or circuit design. Okay. So using these tools, cadence or synopsis or vendor graphics. Raghu, voice is gone. Okay. So I'm speaking very slow. Is this audible now, Raghu? You are able to hear, Raghu? Okay, sir. So try to adjust for few minutes. Okay. So as per generic VLSI design flow, we have logic design, logical verification, synthesis, formal verification, physical design, circuit verification, timing analysis, power analysis, and physical verification. So for this, we have different kinds of tools from EDA vendors or EDA partners like Cadence, Synopsys, and vendor graphics Siemens. So we have Xcelium from Cadence for logic, or VCS from Synopsys, synthesis Genus, and DC compiler from Synopsys, formal verification, and I can write here model from Synopsys, Siemens. Audience? Krishna? Sim Synthesis, I am not aware. So I most famously use it to these tools, Caliber, Audience, Krishna. Yeah. So that's all for today. Okay. So I am ending the session. If you have any questions, Blackbucks team will answer your questions related to assignments, submissions, exams, and everything. Okay. So Blackbucks teams hope the session is completed for today. Okay. So if at all any doubts are there related to subject, please post your questions. I'll explain you how to do that. Karat, you want me to explain?
Sir,
Raghunandan is asking how to attend assignments. So we have given some assignment questions and everything. So they might
yes.
be asking how to submit them and how
Sir,
to
we
take care
have
about.
given like to submit in the PDF format, so we can
Yes, yes.
also correct.
Yeah, Sharath, you explain them for this rest of the 15 minutes. Some
Yeah, okay,
people
sir.
are not aware about it. So as this is a recap session, someone might be joining a freshly or they might have not done the assignments. So please help them to complete assignments.
Yeah, okay,
Okay.
sir. Okay,
So
sir.
I'll leave for the day. Take 15 minutes of time to explain what are the assignments we have given and how they have to submit. Based on their assignments only, we are going to give the gradings also. Okay.
Yeah,
Take
okay,
care
sir.
about it. Thank you.
Okay.
Good night, all.
Yeah, hi guys, is anybody having the doubts about assignments or something? Can you please respond in the chat? I'll be answerable. Yeah, Shivaganesh, you will be given in few days. You will be given the structure of the projects and all. It will take another 2 more days, I think so. Yeah, Pawan, what is assignment? Which assignment do you want me to give clarification about? I think you have to submit in the PDF format. The assignments, the assignment 3, I think so, the latest one. You should submit in the PDF format. Is anybody having another doubts about assignments or something projects? Can you please respond in the chat? Yeah, 1 minute, guys. Jaideep, is there any topics for projects, sir? Yeah, the projects is all about the Verilog codes, I think so. All the 20 questions are about Verilog codes. The topics I'm not supposed to tell, I think so now. In another 2 more days, the Blackbucks team will be given the topics about the projects. Yeah, Janhavi, what is, sir, can you tell us about assessment, assignment, and about it? The assessments are the daily class-based test, I think so. You have to write the assessment day by day. Assignment is the weekly assignment. You'll be given the, I think, two Verilog codes and MCQs or subjective questions is their choice. You have to write weekly assignment. Yeah, Kirtana, assignments, you have to write the Verilog codes and you have to submit in the PDF format. Taran, can you please unmute yourself? Hello, Tarun.
Hi, sir. Okay.
Yeah.
Hi, students. You can write your assignments in the Learn. When you log into your student ID in Tap Blackbucks, you can see in the Learn option, you can see the assignments which you can post in PDF format. Write the codes in, write the write or copy paste the codes in the PDF and copy the simulation waveform results in the PDF and post me in the PDF format. Don't post in links. I cannot access them. Please post them in PDF format. That's all about assignments.
Employability test. Jaideep, write the code in the Word document and make it as a PDF format and post it in the tab. That's it. And we don't have any information about employability test. You can leave it that. So can you please make a video how to do a PDF format? Just write the code in the Word document and convert it into PDF format. That's a simple thing. So when you're writing in the EDA playground, the source code and test bench, copy both the codes and put it in the PDF format. That's it. The simple one. I think Kirtana and Amar got the answer. Leave the employability test. I don't know if you are facing any difficulty in the accessing the Blackbucks. Please contact the admin team. We are not supposed to handle those questions. And I think it's up for the day. Thank you, guys.